Direi un grande applauso a Michele. Allora, Michele è bresciano, esportato in Torino, software engineer in Nebuli e saxofonista. L'altra cosa, invece, non ci parlerà di musica in questo talk, magari il prossimo, o forse, chi lo sa. Di che cosa ci parlerai oggi, Michele?
Acceso, si sente?
Sì.
Sì, ok. Parleremo di GPU, Kubernetes e come andare a utilizzare le GPU in modo efficiente per ridurre i costi, quindi si collega un po' al talk che c'era prima.
Ottimo. Il talk sarà in inglese? O...
Esatto.
Sì?
Sì, ormai l'ho preparato in inglese.
Ottimo.
Andiamo in inglese.
Quindi grazie Michele per questo intervento e ci rivediamo dopo nella sessione di Q&A.
All right, so let's switch to English. Just very few words about me. As Michela was saying, I'm a software engineer at Nebuli, where we are building a platform for monitoring artificial intelligence costs all in one central place and then optimize them. So, speaking of infrastructure cost, the goal of today's presentation is to learn more about how we can increase GPU utilization in Kubernetes so that we can bring down our infrastructure cost. We will start by seeing the different GPU sharing techniques that are available for NVIDIA GPUs, and we will focus only on NVIDIA GPUs because they're basically the industry standard in the artificial intelligence ecosystem. We will then see how to use these GPU sharing techniques inside Kubernetes, so how we can bring them to Kubernetes. And then we will see why we should use instead dynamic GPU partitioning if we want to actually maximize the GPU utilization in our cluster. And finally, we will have a very quick overview of the dynamic resource allocation API, which is a new API that comes with Kubernetes 1.26, and that is going to be the future way for managing shared access to resources such as GPUs. All right, so artificial intelligence, as you know, is on the rise, and it's getting more and more common to have AI workloads on Kubernetes clusters. And the main characteristics of these workloads is that they require GPU acceleration. But some of these workloads, they don't require a full GPU, right? Because if you have a small inference server, it doesn't need to run on an NVIDIA 800 with 80 gigabytes of RAM. And since GPUs are expensive, our goal is to bin pack the highest number possible of these AI workloads into the same GPU, into the same node, so that we need less nodes for running our workloads, and then we can save money. So that's our goal. So if we want to pack multiple workloads on the same GPU, we need GPU sharing. We need a way to share the GPUs among multiple processes. And the main challenge here is memory isolation, because generally you don't want these processes to interfere with each other, right? Because if you have some critical workload, you don't want that workload to crash because some other processes allocated all the available GPU memory. And so if we want to share the GPU, we have 3 different techniques, and each of them offer a different level of isolation. Let's start with time slicing. It's the simplest sharing solution, and processes are executed concurrently. So you have a temporal fair sharing of the computing resources of the GPU. You have the GPU that keeps switching among the processes and executed all of them one at a time. So like a CPU with one core executing multiple processes, it keeps switching among all of them. And it is supported by all GPUs, and it's very easy to implement and use in Kubernetes, as we will see soon. It has a very important limitation, which is you don't have either memory limits nor memory isolation. So you can have a process can allocate all the available memory, and this leads to very frequent out-of-memory error. And also, if a process crashes with a memory error, it can tear down other processes. So this is a very critical downside. And also you have lower performance because the context switches of the GPU, they have overhead, which affects negatively the performance of the processes running on the GPU. On the opposite of time slicing, you have multi-instance GPU. With multi-instance GPU, the GPU is actually split into up to 7 slices. And these slices, they're really physical slices, so they're fully isolated. Each slice gets its own memory and computing resources, so processes cannot affect each other. And these slices are called MIG devices. And each MIG device is described by a MIG profile, which describes the size of the slice. And it does this so using a naming convention. You can see an example below, like 2G.20 GB, which means you have a slice with 2 units of computing resources and 20 gigabytes of memory. And you cannot create the slices as you want. You can only choose between the available MIG profiles on the specific GPU model. And you cannot also create them as you want. You must respect the allowed configurations according to the GPU model you're using. And you have an example on the right, which shows the available configurations for a NVIDIA A100. So you can have the horizontal configuration, you can choose between them, but you cannot have vertical overlapping. So it's not very flexible. The main advantage, of course, is that you have full isolation, which is very convenient in some use cases. And also, in this case, processes are executed in parallel. So you don't have the context switches overhead, and you have higher performance compared to time slicing. However, multi-instance GPU is supported only by Ampere and more recent architecture. So there are not that many GPUs with which you can use MIG. You have low flexibility because you cannot choose your own slices. You can only choose between the available configuration, which is quite limiting. And also, you have a coarse-grained partitioning of the GPU. For instance, on NVIDIA A100 with 80 gigabytes of memory, the smallest available slice has 10 gigabytes of memory, which is quite a lot. Halfway between time slicing and MIG, you have MPS. MPS is a client-server implementation of the CUDA API. So you have a server running on the GPU, and it manages the access to the GPU. So you have clients that instead of going directly on the GPU, they make requests to the MPS server, and the MPS server manages the access and shares the resources among the processes. So it's very easy to set memory limits or set computing limits on the different clients. And it's very flexible, so you can have the size, the slices, the size you want, because it's just configuration of the server. And in this case also, you have spatial sharing of the resources. So processes are actually run in parallel, and you don't have the context switch overhead. So also in this case, you have higher performance compared to time slicing. However, you don't have error isolation. So you can still have a process that affects the other. By, for instance, crashing with a memory error, it can still affect the other processes. So, main advantage is high flexibility. You can choose the slices you want, it's very flexible. Processes are executed in parallel, so you have higher performance compared to time slicing, and you have memory limits. And also it is available in basically all the modern GPUs. However, you don't have full isolation, and also integration is not straightforward because you have the MPS server in the way between the client and the GPU, and this is not totally transparent to the client, so you have to make some modification. So here's a quick summary of the 3 different techniques. They are sorted by isolation level. On the top, you have time slicing, isolation level 0. You don't have it. And however, it is supported by all GPUs, and it's very easy to use. Half-wave, MPS, you have memory limits, but no full isolation, and it's very flexible. And finally, you have MIG, you have full isolation, but coarse-grained partitioning and supported by a few GPUs. Also here, you have a performance comparison between the 3 different techniques. And here we run inference requests on a YOLO model on a single GPU on an NVIDIA A100 with 80 gigabytes of memory, and we increased the number of pods sharing the same GPU up to 7. So if you look at the rightmost column, you can see that when we had 7 pods, the performance of time slicing compared to MIG or MPS were almost 2 times slower. So the average inference time was very, very higher. So the context switch overhead is actually quite relevant. So we have seen the 3 different sharing techniques for GPU. How do we bring them to Kubernetes so that we can use them in our cluster? Well, first of all, we have to enable GPUs in our containers. How do we do that? We need to install NVIDIA drivers on the host, of course, and the NVIDIA driver container toolkit, which includes the container runtime and makes the GPU available to the container. Here we have 2 options, manual installation or better GPU operator, and it does that for us. Once we have GPUs available in the containers, we need to make them available to Kubernetes. So how do we do that? This is done with device plugin. The device plugin framework is a Kubernetes framework that allows you to expose custom resources to Kubernetes without changing the Kubernetes code itself. So you have a framework, a set of plugin, which is everyone can write its own plugin, and it's up to the resource vendor to implement them. And the device plugin manages the allocation of the new resources and the advertisement of these resources to the kubelet so that they are available to Kubernetes. And these resources are exposed as extended resources. And the main characteristics of the extended resources is that their quantity can only be integer, so they're exposed with integer numbers, and they cannot be overcommitted. So when you request them, the limits must be equal to the request in the field. You have an example on the right. You have a pod requesting a single NVIDIA.com GPU. And we specify only limits because we cannot overcommit them, so it must be equal to the request. The main challenge here is how do we share a GPU? If we expose them as integer resources, how can a container ask only for a fraction of GPU? So how do we do that? The solution here is to expose the same physical GPU with multiple resources. So if we have a single GPU, we can expose it as 4 GPU resources using integer numbers. And this is managed by the device plugin. So it's just a device plugin configuration. Here you can see an example for time slicing. You have the NVIDIA device plugin running on the node, and you can configure it to expose every single physical GPUs as 4 replicas, for instance. So if you use that configuration and then you describe your node, you will see that you will have 4 GPU resources instead of 1. Sometimes you don't want to, you want to distinguish shared resources, shared GPUs from physical ones. And you can also do that just by configuring the device plugin. You can set the parameter rename by default. And in this case, the resources are exposed as GPU.shared. So the name changes, and then your pods can request that resources if they can run on a GPU shared with time slicing. Otherwise, if they want a physical full GPU, they can keep requesting nvidia.com/GPU. For MPS, it's very, very similar. We still do that with device plugin configuration. The problem here is that it is not available on the official device plugin from NVIDIA, but is available on a forked version of that plugin, which deploys an MPS server together with the device plugin daemon set. And again, we just specify how many replicas we want for a single GPU. And we also specify, in this case, the memory limits for those slices. So in this case, it's a bit small. Maybe, I don't know if you can see here. We can also specify memory GB, which represents the memory limit that each slice will get. So if we describe our node here, the node has just 1 single GPU. But if we describe it with this configuration, we will see that it has 2 GPU-2 GB resources. And each of these resources has a limit of 2 GB of memory. Here we can see that MPS is not totally transparent because we have two constraints. First of all, we need to run the containers in the host IPC namespace because MPS servers and clients communicate with intra-process communication, so they need to be run in the same IPC namespace. So we need to specify host IPC to true. And also, MPS requires that the clients run with the same user ID as the MPS server, so which is 1000 by default. So we also need to specify run as user 1000 for our containers if we want them to connect to the MPS server. Finally, we have MIG, same as the two befores, just device plugin configuration. We can choose whether to expose the MIG devices, so the GPU slices, as standard nvidia.com/GPU resources, or with a different name which contains the MIG profile, so the size of the slice. But this assumes that you already have the MIG devices on your GPU, right? So how do we manage them? How do we create GPU slices? How do we delete them, and so on? We have three options, basically, for doing that. The first option is not really an option. We need to SSH to the node and listing the available configuration using the NVIDIA CLI, and then create and delete the devices manually. And after that, we need to restart the device plugin. So it's very cumbersome, not really an option, not user-friendly. So not really an option. Option two, slightly better. We can use MIG Parted. It's an open source tool from NVIDIA. Basically, you can just define your configurations into a YAML file where you specify different partitionings for your GPUs, and then you can apply them just by running a command and specifying the name of the configuration you want to apply. Slightly better, but you still have to SSH to the node and then restart the device plugin, so not very scalable, not very in the Kubernetes way. Third solution, still better. We use an operator. So this is a thing that we can easily automate, and we do that with an operator. So we use the NVIDIA GPU operator. We take the MIG parted configuration, we put it into a config map, and when we want to apply a partitioning configuration, we just apply a label on the node, and that configuration gets applied. So our slices are created. And this is scalable, but it's not optimal, right? Because I still have to manually apply the labels. I still manually have to know which configuration I want to apply, which is not trivial. And I also need to check which of the current slices are being used, because I don't want to delete slices that are being used by containers, right? And this is a problem which is common also to the previous two sharing techniques. They all rely on static configuration that the user has to manually define. And this is a problem because static configuration causes poor usability. Because how do I know which is the optimal sharing configuration? And the optimal configuration might change over time, right? Because pods requirements, containers requirements change over time. So the GPU slicing must adapt to what the container requests. It cannot just be a static configuration. When you have static configuration, you have generally lower GPU utilization, and at the same time, you have pending pods that cannot be scheduled due to the GPU slicing resources that are requesting that are not available. So here's an example to make this a bit more clear. Let's say that at time T1, I have some training workloads on my cluster. I'm running training of big models. I need a lot of GPU memory, so I configure my GPUs to expose big slices with 40 gigabytes of memory. And I also have, for some reason, I have some inference servers on the same cluster. Maybe I'm doing some tests, and I just require few GPU memory, so I expose just a few 5 gigabyte of memory slices. So I have many 7G.40G slices and just a few 5 gigabyte slices. However, at time T2, the training workloads end, and for some reason, the inference workloads increase because maybe an autoscaler kicks in, or maybe I just deploy more inference servers. And the problem is that the configuration of the GPUs doesn't change. So I still have many 7G.40GB resources and very few 5 GB slices resources. So my new pod cannot be scheduled because the inference servers request 5 GB resources. And at the same time, my GPUs, they're not being used because they are being exposed as 7G.40GB resources. And this is the main problem. So how do we solve it? We can solve it with dynamic GPU partitioning, which consists of automatically updating the partitioning configuration according to the requirements of the workloads currently running in the cluster. So partitioning is done in real time without any manual intervention required. And in this way, you have higher GPU utilization because the optimal sharing configuration is always applied. You always have, when it's possible to create them, the GPU slices that are required by your workloads. And also you have lower operational costs, right? Because you don't need anyone to go there and update the configuration, choose the right one, update the labels, and so on. And the problem here is that the official NVIDIA tools do not support dynamic GPU partitioning. They just rely on static configuration, both the GPU operator and the device plugin. So how do we achieve dynamic GPU partitioning? We can use NOS, which is an open source operator, and it is meant to run AI workloads efficiently on Kubernetes. And it runs alongside the NVIDIA device plugin and also the GPU operator if you want, but it's not a strict requirement. And it has two main features, one of which is dynamic GPU partitioning. The other one is elastic resource quota, which allows you to set quotas on namespaces. And if a namespace is not using quotas, it can lend its quotas to other namespaces, but that's not the topic of today's presentation. We will focus just on dynamic GPU partitioning. So you can see NOS as a cluster autoscaler, but for GPUs. Instead of scaling the number of nodes, it watches the pending pods and scales the partitioning configuration of the GPUs of the cluster. And this ensures that the optimal partitioning configuration is always applied. Actually, it's not really the optimal because it's a big packing problem that we are solving with a heuristic. So it's not really the optimal solution, but it's pretty close to it. And it supports both MIG and MPS. However, it doesn't support time slicing. And with NOS, you just submit your pods to your Kubernetes cluster. You have containers requesting GPU slices, and you don't have to worry about creating those slices. They are automatically created by NOS operator. And you have an example on the right where we are requesting some MPS resources in the first manifest and some MIG resources in the other one. And that's all we have to do. And besides NOS, well, there are other ways to achieve dynamic GPU partitioning, because why do we need to rely on an operator for having something like this? This should be inside the Kubernetes API, right? The same way we manage persistent volume and persistent volume claims. We don't need an operator for doing that. It should be inside Kubernetes controllers. And this is the reason that now we have, with Kubernetes 1.26, we have the dynamic resource allocation API. And it is a generalization of the persistent volume API, but for generic shared resources. So this API introduced some new resources, which are resource class, resource claim, claim template, and pod scheduling context, which is used for deciding how to schedule pods by the specific implementation of the dynamic resource allocation. And it's very similar to the device plugin framework. So the dynamic resource allocation API is basically a framework, and the specific vendors of the resources need to implement their own DRA drivers. And for GPUs, we have NVIDIA that is currently implementing their own DRA driver. And it's still under very active development. You can play with it, but it's not production ready. But it's already quite fun to use. Maybe I can zoom in a little bit. So basically, you have pods requesting GPU claims here in the resources. So here we have two pods. They both request a GPU claim. And then I have to define my resource claim resource, which is called GPU claim in this case. And here I specify the resource class name, which is gpu.nvidia.com, so that the DRA will use the NVIDIA DRA implementation for provisioning that claim. And here I can also specify the parameters for the claim. And here I say that I want a MIG slice with 10 GB of memory. And then here I define my parameter, which links the name 1G.10GB to a MIG profile with 1G.10GB with that name. And that's all I have to do. I don't have to manually create the slices. I just omit my pod with those claims, and similar to what happens to persistent volumes and persistent volume claims, those slices are provisioned automatically. Yeah.
So the resource on the left-hand side is Kubernetes.
Yeah.
The one on the right-hand side is a custom resource definition by NVIDIA.
Yeah, exactly. The parameter of the resource claim are custom resources up to the vendors. So they depend on the implementation. Here you can see when you specify the parameters, you specify the API version and the kind. So that's the custom part. In this way, vendors can customize the resource allocation and the resource provisioning. So it's very flexible as a framework. So wrapping up, how do we improve GPU utilization? We do that by GPU sharing. And the main challenge here is memory isolation and memory limits, because we don't want out-of-memory error. However, the problem with GPU sharing using standard NVIDIA tools that are available at the moment is that they rely on static configuration. And static configuration are not enough if we want to achieve operational excellence. So the solution here is to have some form of dynamic GPU partitioning. How to do that? Two ways: either custom operators, such as NOS, or we can rely on the Kubernetes API as soon as the drivers will become available. So in this case, dynamic resource allocation API. So higher GPU utilization means we can schedule more pods with less nodes. And what do we do with spare capacity? Well, we can either scale down the cluster if we want to save money, or schedule more workloads. For instance, if we are on-premise, we cannot scale down the nodes. We can, however, use the spare capacity for running more workloads. So, if you have any questions, I'm available. And
Any of you has question for Michele? Do you hear me? No? Sì? Vai, aspetta. Vai.
La faccio in italiano?
Facciamola in italiano a questo punto.
Ok, vai.
No, niente, siccome ho trovato la presentazione interessante, volevo sapere se avevi scritto qualche blog, post, eccetera, eccetera, se poi in qualche modo lo puoi condividere, non so se
Sì, ho scritto qualche articolo su Medium.
Ok, quindi basta che cerchi il tuo nome.
Sì, se cerchi, torniamo all'inizio.
C'era
in effetti non ho messo i link, ho messo solo quelli a GitHub e Twitter, però se cerchi Telemaco 019 su Medium,
ottimo, allora li cerco, no, perché siccome volevo provare un po' su AKS, quindi su Azure. Okay,
sì, lì ci sono proprio step by step tutorial in cui riprendo proprio la documentazione, faccio vedere un caso
ottimo,
d'uso.
Perfetto, no, siccome mi aspetto che andando avanti c'è un'esplosione incredibile delle AI, quindi io peraltro appunto lavorando con Microsoft con OpenAI ti puoi immaginare, e quindi mi aspetto che ci sia anche un'esplosione delle richieste di applicazioni che girano su Kubernetes e che usano il GPU.
Sì,
e quella appunto dello sharing delle GPU è un grosso problema.
È un problema molto diffuso da quello che abbiamo visto, e difatti anche l'operator ha avuto abbastanza diffusione, c'è molta gente che lo usa e ha ancora un po' di problemini, però insomma è una cosa che torna molto utile a diverse persone da quello che abbiamo visto.
Io volevo chiederti, run e AI se lo conosci, ci
Sì,
stavo un po' guardando.
Conosco benissimo.
Ok, e ricade in questa area, no? Cioè viene utilizzato proprio per fare il frazionamento dinamico delle GPU.
Esatto.
Ok, rispetto a quello che ci hai raccontato come si pone, cioè siamo su quella strada, ci sono delle differenze, se mi racconti.
Sì, la differenza principale è che la loro è un enterprise platform e non è open source, mentre questo è un operator open source. E ovviamente loro offrono tutte quelle feature enterprise che un operator open source non offre. Però il concetto di fondo del dynamic partitioning che c'è in NOS e che c'è in Run AI è lo stesso. Quindi la feature core è la stessa, solo che questo è open source.
Sì, vabbè, allora una domanda me l'hai rubata tu, va bene. No, era per sapere, quindi Run AI si posiziona al pari di NOS, se ho capito bene.
Sì, però risolvono lo stesso problema. Ovviamente Run AI, essendo un enterprise platform a pagamento, offre anche feature in più. C'hai un portale web, c'hai una CLI, hai la differenziazione tra tante cose in più.
Però chiaramente NOS è su GitHub, è open source, quindi innanzitutto c'è questo che ha un grandissimo valore, ovviamente.
Sì, vediamo se riesco. Ok, sono senza internet. Volevo aprirlo. Sì, l'abbiamo testato su AWS e Azure e anche su GKE. Abbiamo avuto alcuni problemi su GKE. Nel Discord della community ci sono alcuni utenti che lo stanno utilizzando su GKE, ogni tanto hanno qualche problema. Adesso stiamo cercando di raccogliere un po' tutto in modo da includerlo nella documentazione, però dovrebbe funzionare anche lì.
Invece l'altra mia domanda, quello che non ho capito io, è se quello che adesso NOS o Run AI fanno a tendere va a finire nel DRA oppure ci saranno sempre alcune DRA e implementerà alcune cose che poi avranno sempre necessità di una platform esterna che lo deve gestire. Non ho capito se è solo una questione di sviluppo oppure ci sono funzioni distinte.
Guarda, ti dico la mia opinione. Secondo me la parte di partitioning core andrà sul DRA, come è per i persistent volume claims. Ha senso che sia una cosa dentro Kubernetes. Diventa bello poi costruire on top a questa feature, quindi andare a fare degli operator che vanno a sfruttare queste API per fare cose un po' più interessanti, come ad esempio l'autoscaling, piuttosto che gestire i tipi di AI workloads in modo diverso, perché una cosa è un training, una cosa è un inference. Il training posso ad esempio interromperlo, quindi posso avere l'operator che magari me lo va a gestire in modo diverso. E quindi secondo me esisteranno ancora platform come Run AI, esisteranno ancora operator come NOS, e andranno a fare cose magari più avanzate sfruttando il concetto core che sarà mosso dentro Kubernetes.
E io volevo chiederti una cosa sul time slicing. Non ho capito se il parallelismo è reale o se viene implementato una sorta di round robin sulla GPU.
No, non è parallelo, è concurrent, quindi è esattamente un round robin. Hai la GPU che continua a switchare velocissimamente tra i vari processi, come una CPU, quindi una CPU con un single core che esegue più processi, allo stesso modo.
Okay, grazie.
Di nulla.
Altre domande? No? Allora, ancora un grande applauso a Michele.
Thank you.